Alright, silly people, here's the situation. This time we're going to be doing the binary search method to solve this equation down here. But the context of the equation is Planck's radiation law, and we're trying to find that the maximum emitted radiation uh, given a wavelength lambda is given by this equation analytically, and then you can plug in substitution to make the equation read like that instead of this garbage. So it is kind of, it's kind of a tough integral or a tough derivative if you don't know what you're doing. I'm going to delete this code before I scroll down too far. But yeah, you start off with the intensity formula that was up there. You just take the derivative of it with respect to lambda, set it equal to 0 to find the maximum. You will have to do a little bit of quotient rule derivative stuff, and also after even doing that, you're going to have to redistribute the terms, do a little algebra on it to get it down to that form. But all of those steps are here. I won't explain it too much, except it's really useful that you can just multiply the whole equation by this term, and so you don't really have a denominator, and then you can divide the equation by lambda to the -6, and also 2 pi hc squared. If you do all of that, then you get this form of the equation, which is the one that Newman wanted you to get, right? This guy. Then you make the substitution of hc over lambda kpt equals x, and so you just very easily plug that into your equation and you get this form, which is much nicer to look at. And also just rearranging the substitution, you can put it in terms of lambda and then turn that into b over t, with b equaling this thing. So now we can get into the coding part of the problem, which is, again, to find the solution to this guy using binary search method. And so I'm going to go ahead and import numpy as np, as always. I'm going to define a function f of x, where it's going to return the left-hand side of this equation up here. So it's going to return 5 times the exponent of minus x plus x minus 5, right? The idea of binary search method is you start with 2 initial guesses that you think are going to be on either side of the solution to the problem, right? So for this, I found that a nice pair of starting points is x1 equals 2 and x2 equals 8. Also because I know what the solution of the problem is, that works. And also I'll say that the problem actually does have a trivial solution at x equals 0. If you plug in x equals 0 in here, then you're going to have -5 plus 5, which is 0. So don't use 0 as your lower bound or anything lower than 0. You definitely want to use positive numbers. The way to check, though, if your guess is good, is if the function at x1 and the function at x2, if they happen to not match signs. So if the multiplication of the two is less than 0, then that's a rough guess. So I'm just going to have this print rough guess if they happen to not match signs, right? Otherwise, you can get into the loop. You can define an accuracy. Newman wants us to get it accurate to 10 to the -6, as always. I'm going to set an error to be something really large to start with, and then start the error loop while it's greater than the accuracy. What you want to do is you want to calculate a midpoint between x1 and x2, which is just going to be given by x1 plus x2 over 2, right? At this point, what you're going to check is, again, you're going to check if f of x1 and f of x2 match signs. Let me actually read it directly from the book just to be sure. Yeah, you check if f of the midpoint, so f mid, has the same sign as f1. So if f of mid times f of x1, if it's greater than 0, that means that they do have the same sign. Then you set x1 equal to the midpoint. Otherwise, you set x2 equal to the midpoint. And then you check your error. This time the error, you can just have it be equal to the absolute value of x1 minus x2. And at the end, the solution to the actual equation will be the midpoint of the last two things that you find. So x1 plus x2 over 2 again. And we can print the solution like that. And I think I actually need to flip the sign of this. But yeah, because you have to have, you have to make sure that the initial f of x1 and f of x2 have opposite signs. But this did actually work. That is the solution to the problem. It's 4.965. Verified that via Desmos. And so the next part of the problem is to use that solution to calculate the surface temperature of the sun, which is when we're going to put all these constants back in. So H is the Planck's constant. It's 6.626 e to the minus 34 joules times seconds. And then the C, speed of light, is just 388 meters per second. KBT, or KB, Boltzmann's constant, is just 1.38 times 10 to the minus 23. And so you're going to use this to calculate what, you have x, so you can use it to calculate b. So b is h times c divided by kb times x, or the solution actually. And then once you have b, then you can plug it into the Wien's displacement law, but then solve for t instead of lambda. So you're going to do b over lambda, and the wavelength of the light from the sun is actually just 502 nanometers. So t will be b over lambda, and we can print out the temperature of the surface of the sun, and we get something that is close to the right answer. It's about 5,800 Kelvin. So pretty nice stuff here.